So now let's continue with the thermal imprinted lithography. So we'll talk about reverse imprinted lithography and imprinted lithography with the bulk resist. So first let's look at reverse imprinted lithography. So we know that normally when we do the imprint, so we coat the resist onto the wafer. But for the reverse lithography, so we coat the resist on the mold. The mold has low surface energy. The mold has low surface energy, and the wafer substrate has a high surface energy. As a result, so you heat up so that the resist will become sticky. So after separation, so the resist will go to the substrate detached from the mold because the substrate has higher surface energy. So for this transfer process, here we effectively transferred the resist pattern from the mold onto the substrate. So we can do this on the pre-patterned structures. So in this case, we transfer the greeting pattern onto this onto another larger greeting pattern. On the right side, so we have the high aspect ratio PLMA pillars by this reverse lithography process. So the requirement, so one of the issues is that so because the mold, the mold has a low surface energy. So we have a low surface energy, the spin coating may be difficult. So for the spin coating to work, normally we have a low surface energy, so the resist, the resist may have this shape. So this means that they will not white. So what we need? We need the resist to be something like that. So it is white. So we need it to be white. So how to make the resist white, a low surface energy area? So the solution is to use the non-polar solvent. So here we have the toluene. So we have this one. So this one is non-polar. The chloroform is also non-polar. For the other popular resist like anisole. For this one is popular solvent for spin coating anisole, but this one will not work because here we have this oxygen, so we have the polar group. We have polar group, you get higher surface energy. So because the resist white the mold, so the resist will fill in the mold cavity by the capillary force. So this way we do not need we don't need a pressure. So because we don't need a pressure, there is no shear stress. There is no shear stress. So when there is no shear stress, so the separation between the mold and substrate will be easier because when we do not need a pressure to squeeze the resist into the mold cavity. So we can keep doing the same process. So in this case, we did first reverse lithography, the second reverse lithography, third reverse lithography. So we can have a stack of the 3 layers of the patterns. So the requirement is obviously when we do the later on process. So when we do the third layer, the glass transition temperature of the later layers should be lower than the previous layers. So this way we can do the transfer of the resist pattern at a lower temperature so that the previous layer will not be melted. For the application, the application for this kind of structure, looks good, but the application is not so clear. So if we can do the alignment, so if we can do the layer by layer stacking alignment, then it will be very useful. So this can be used for the photonic crystal. We can do the alignment, we can make it a photonic crystal. But here for the thermal print, because of the thermal expansion, alignment is not easy, so it will not be useful for the photonic crystal. So here is the easier setup to do the hot embossing of the pellet. So you just need a hot plate. You have the pellet, you have the mold, and you have the wafer. You press. It's very easy to get some macro or even nano structures. You can, as you see here, so we put the pellet, we press another wafer, press onto another wafer, then we cool down, we separate, we get this one. If we do one more step, so we can have this polymer structure got sealed to another sheet. So when it's sealed, this part is the fluidic channels. So this can be used for the microfluidics. So as you see here, so here's the example of the PLMA. So we use PLMA pellet. PLMA, you can see those microstructures can be used to make the macro or nanofluidic channels. So we can do the same process for the polystyrene. Polystyrene is also a thermoplastic polymer, so we can do the same thing as the PLMA. So the good thing for the polystyrene is that it is biocompatible. So because the cell culturing petri dish, the petri dish is made of polystyrene plus some additives. But actually, those additives is also very important for the cell growth. So when we have the greeting structure in the polystyrene, so we can grow the cell. You can see when we have the cell growth on those greeting structures, the cell will be elongated. The cell will be aligned. So this is called a contact guided of the cell growth. So in our human body, so almost all the cells, they are elongated, so they are aligned to the sublayers or substrate. But there are some cells that is not aligned. And what cell is not aligned? What cell is not elongated? That's the blood cell. So the blood cell is circular shape because this blood cell is not attached to any substrate. The blood cell is circulate in the blood. So this one is circular. But for the most other cells, it is elongated. But for the tissue engineering, in tissue engineering, if we want to repair a tissue, so we want to grow the cell that is the same alignment as what happened in the human body. For the tissue engineering, what do we do? So we grow the tissue outside of the body, then we transplant the growth tissue onto the human body. This is the tissue engineering. So we need the cell to be aligned in order to transplant it into the human body. So this work is this is my work. So in collaboration with the University of Laval in Quebec, so we have grown the cornea cell. The idea is that when we have the damaged cornea, so we grow the cornea cell in the petri dish. Then later on we transplant the cornea cell to the human body to replace the damaged cornea. So you can see, so we have the greeting. At day 1, so this one is aligned, so the cell is aligned with the greeting. So dermal cell, so the skin cell is also gets aligned. But for the day 12, so we grew a second layer in day 12. This one, you see this direction. So it is a 60 degree relative to the first layer. And this is actually what happened in a natural cornea. So later on, we did the experiment in the rabbit, but we didn't do the experiment in the human eye. But this one is for the dermal cell. After 12 days, the upper layer of the dermal cell, they are no orientation. So only the bottom layer they got aligned. The upper layer they are not aligned for the skin cell. So now let's look at. So we finished the thermal imprint. So now let's look at UV Curie imprinted lithography. So the idea is simple. So we have the room temperature, low pressure. We will see later on why we can have low pressure. So the resist is a liquid. That consists of the monomers, photoinitiators, coupled agent, surfactant, and solvent. So when we shine the UV light, so the resist got cross-linked, got cured. This way it becomes solid. Then we can separate. So the mold here has to be transparent to the UV light. So normally it will work well with the quartz. Quartz is the popular mold material. But another popular material is the polymer. So like a PDMS or thermoplastic polymer, so they are also good transparent materials for the UV imprinted lithography. So the key advantage for the UV imprint compared to the thermal imprint is the alignment. For the thermal imprint, alignment will be very difficult because we have the thermal expansion. So the thermal expansion will destroy the alignment. But here we do at the room temperature, no heating up or cooling down, so we do not have this thermal expansion problem. For the resist, the thermal imprinted resist is closer to the optical lithography resist. For example, a PLMA SU8, and SU8, they are both thermoplastic polymers. They are also UV lithography. They are also photoresist. But PLMA is resist for the deep UV lithography. But those materials, they are not UV lithography resist because they are solid. For the UV resist here, we need liquid. But those photoresist, they are solid. They are very different. So there are a few two ways to do the UV lithography. The first one is called step and flash lithography. As the name indicates, we do the step by step. You can see here. So first, we use the optics. We look at one side, look at the mold, another side, look at the wafer. We do the alignment. Then we take the lens out. So we do the inkjet. to give a drop, to put a drop over the resist onto the substrate. Then we do the pressure, we do the UV exposure, we separate, then we move the wafer, we do another place. So this work is mainly done by the company called Molecular Imprint. But this is the company from the university. This is the spin-off company from the University of Texas, Austin. So the professor is Grant Wilson. So he used to work with the biolab. So he is more familiar with the semiconductor industry. So that's why he had this process. As you can see here, this is why we do it die by die. So we do the one place, then another place, then another place. This is similar to the deep UV stepper. It's similar to the deep UV lithography, it's die by die, rather than do the entire wafer at the same time. This is favored by the semiconductor industry because you do it die by die, similar to the UV lithography. But this company got bankrupted in about 2015. So this company got bankrupted. So they want to sell this technology to the data storage, like a Seagate, Western Digital. Those data storage company, but later on, those companies, they decided not to work on the bit pattern recording media, so they will not buy the molecular imprint equipment. That's why this company bankrupted in 2015. So later on, because it is sold to Canon. It's sold to Canon. So we know the Canon is the Japanese company, so you must know about Canon printer. But Canon, they also make optical lithography in the 1990s. So they make the deep UV lithography scanners. So that's why this company bought Molecular Imprint in about 2015. But this is good for the production, but not good for research, because when you do the inkjet, this layer is hard to control. Sometimes you get higher volume, sometimes you get lower volume. For research, we better to do the spin coating. So this is the this is spin coating. So here are the examples of the snap and flash lithography. So here 30 nanometer. Here 30 nanometer lines, 20 nanometer lines, 65 nanometer pillars, 40 nanometer holes, the 3D structures. This is etched into the silicon. So in principle, the UV imprinted lithography should have lower resolution than similar lithography because of the resist shrinkage. But in reality, we got similar resolution for the UV imprinted lithography and the thermal imprinted lithography because we use thin layer. So when the film is very thin, so the shrinkage will not be a big problem. So as we said, for this inkjet system, we got drop by drop, but this is why it's not so easy to control. If we do the spin coating, when we do the spin coating process, it will be easier to control. But this is the product from the company Nanonex. But this one is the spin-off company from the Princeton University in New Jersey. As you can see here, so here we have the top layer here. It is the UV resist. So we have a thick underlayer. The underlayer is PMA or ARC. The ARC is the anti-reflection. It's called anti-reflection coating. This one, when we do optical lithography, we want to reduce reflection at the wafer surface to remove the interference effect. So that means this layer here is a polymer layer that will absorb the light, so the light will not be reflected. So it's also a polymer layer. So here, why we need this very thin layer? So when we have very thin layer, we get smaller shrinkage. We get minimum shrinkage effect. So because when we do the UV imprinted lithography, so when the resist gets cross-linked, there is about 10% volume shrinkage. If the film is very thin, then the shrinkage will be less of a problem. So the resist here contains silicon. So when we do the oxygen plasma, so the silicon will become a silicon dioxide. The silicon will become a silicon oxide. So this silicon oxide will be resistant to the etching. As a result, we can use the UV resist as an etching mask to etch into the sublayer, that is the polymer layer. The this one is the more reliable than the snap and flash lithography because we can get uniform residual layer film thickness. Then we get uniform residual layer thickness. The this one is more popular for the UV imprint. So because the UV imprint is done at at low room temperature and low pressure, so we can use some flexible and plastic mode. In this case, we use the PDMS mode. I think you know about PDMS. This is the polydimethyl siloxane. It is flexible and soft. Because it is flexible, so we can have conformal contact on the non-flat surface. So we can do the imprint on the curved surface. But this one, because it is too soft, so it's not good for the high resolution. So when we have a smaller feature size, for example, if this is the PDMS, we get, let's say, 100 nanometer. If this pattern 100 nanometer, so when you do the imprint, so the pattern will buckle, will collapse, because this material is too soft. So one solution for this one is to use the bilayer. So we have the PDMS layer here. You have another hard layer here. You have another hard layer on the top. So this way you make the pattern. You make the pattern on the hard layer, so the pattern will be mechanically strong in the hard layer, but we still have this flexible bottom layer for the conformal contact. So one advantage for the PDMS is that because this one S is the siloxane, so this contains silicon. This is the siloxane. So after oxygen plasma treatment, so the top surface will be a silicon dioxide. So this one is good for the anti-snaking treatment. So we will see anti-snaking treatment later on. So again, so because the UV imprint is there at the room temperature and the low pressure, so we can use the thermoplastic mode that has strong mechanical strength. So in this example, this one is ZEP. So we know the ZEP is the popular electron beam resist. That means we do the electron beam lithography, then we do the development. We do even lithography, we get development, then we get the ZEP structure. So we can use this ZP structure directly to do the imprint into the resist, into the UV curing resist. So it will work well, but the problem is that those materials is not good for the anti-snaking surface treatment. So here we have the oxide. So when we have oxide, it is good for the anti-snaking treatment. So when we have the polymer like ZEP, it's not good for the anti-snaking treatment. As a result, those kind of modes may be used for once or maybe twice, but cannot be used for many times because the resist will peel off because the mode will peel off the resist from the substrate. So you cannot get a low surface energy. So we will look at anti-snaking treatment later on. So here's the comparison between the thermal and the UV imprinted lithography. So for the resist, so we use the thermoplastic polymer like a PLMA or polystyrene or thermoset resist. That is thermal cure resist. For the UV imprint, for the resist we know is the monomer photoinitiator and additives. Additive like a coupling agent, silicon, those additives. So the resolution, they can both get very high resolution. Here I said 5 nanometer. If you can make the most 1 nanometer, then you can make 1 nanometer resolution. This one 2 nanometer, because this one they use the carbon nanotube. Carbon nanotube is 2 nanometer, but it is difficult to make the 2 nanometer structures by lithography method. This one at higher temperature, normally 30 to 100 degrees above glass transition temperature. This one room temperature. This one we need thermal imprint. We need a higher pressure to overcome the acidification. This one we use a low pressure. We will see why we can use low pressure later on. So this one the resist normally done by the semi coating. This one semi coating or drop use the inkjet dropping. So the thickness can be many micrometers, can be very, very thick. It's like a hot embossing process. Here is typically less than 100 nanometers because of the shrinkage of the cross-linking. If you have a thicker resist, the shrinkage will make the resolution bad. You need a thin layer to avoid the shrinkage problem. But when you use a thin layer, you need an extra transfer layer and another layer below the top layer, as you see here. So we need this under layer below the top resist layer. So the cycle time, this one we need heating and cooling take a long time. This one, no cooling, no heating, a short time. The large feature is difficult because the flow is difficult. This one is easy because the UV resist is liquid. The liquid has very low viscosity. For the alignment, this one is difficult. For the thermal imprint, alignment is difficult because of the coefficient of the thermal expansion. This one people have demonstrated 20 nanometer alignment. So for the application, this one can work with the many different materials and easy and can work with many different materials. This one is targeted for the semiconductor industry with the alignment. But actually, nowadays, people use more and more UV imprinted lithography than the thermal lithography, not because of the alignment, but because of it is very fast and very easy to work with. This one is more and more popular, but this one, for research, this one is easier. So now let's look at the UV lithography resist. So the resist, as we said, has little in common with the photoresist. The photoresist, like SU8, so they are thermoplastic polymers, not liquid. But this one, we need something liquid. So it's very different from the photoresist. So in principle, any materials that is soft, that can be imprinted, so it can be imprinted, and it can be hardened by the UV exposure, can be used as the UV lithography resist. For example, the UV glue or dental sealant, those materials, if you want, it can be used as the UV lithography resist. So there are two types of the photoinitiators, cationic photoinitiator and free radical photoinitiator. So we have said that, so for the UV imprint, we can use very low pressure, only like 1 atmosphere versus 10 atmosphere for the thermal imprint. So why we can use low pressure? So this is one because the resist is designed that it will wet the substrate. So when it wet, in principle, you do not need any pressure because the resist will fill in the pattern on the mold by the capillary force. It will get in by the capillary force. You do not need to apply any pressure. But in reality, you will need some pressure, like 1 atmosphere pressure, to make sure that the mold and the wafer, they have good contact. So the pressure needed only to make sure you have good contact, not to squeeze the liquid into the pattern on the mold because they wet each other. So on the other hand, so we want easy separation. Easy separation, that means the surface energy here has to be low. So we have low surface energy and easy separation. So how to make it white and easy separation? So you can see this is the formula. But this cosine phi term is positive. This is positive number. This number is very small. Then the solution is that both the resist and the surface, both the mold and the resist, they have low surface energy. Then this way it will white and also easy separation. So one issue is that because the surface energy is very low, we have very low surface energy, so the semicoating may be difficult. Because, as I said, it's like a kind of hydrophobic, not low surface energy. Semicoating may be difficult. And also there may be resist peeling off. The surface energy is too low, the resist may peel off from the substrate. So one way to solve this problem is to have this underlayer. So when we have the PMA or PMDI, polydimethyl glutamate ARC, anti-reflection coating layers. So when we have the underlayer, those polymer layers, they're not as smooth as the silicon, and also they have a high surface energy. They have this underlayer. So we have this underlayer. The semicoating will be less of a problem because, as I said, the polymer, they are not as smooth as the silicon. Here are the examples of the UV imprinted resist. The first one is based on the free radical polymerization. So we have two types: the free radical and cationic photoinitiator. The first one is the free radical polymerization. This one we can use the acrylate precursor. This is the acrylate precursor. So it has great reactivity. That means higher curing rate, with large choice of the monomers and oligomers. The problem is that this free radical polymerization is inhibited by the oxygen. So we have to do the lithography in a vacuum, in a natural environment, or somehow we need to use the soft mode. To drive the air out before we do the imprint. This is the free radical polymerization. Another one is the cationic. So this one, cationic photoinitiator, or the cationic polymerization. There are two choices. One is the vinyl ether. So this is the vinyl ether. The other one is the epoxide. The advantage, this one is not sensitive to the oxygen, so we can do the UV imprint in the air. So it's not sensitive to the oxygen. The problem, for the vinyl ether, the cost is high. We have higher cost, a smaller choice go the monomers and oligomers for the vinyl ether. For this one, for this epoxide, this one, the curing rate is low at the room temperature. So those are the main components of the UV resist. There are other additives. We have the cross-linker. But normally we have the polymerization, you get linear polymer. So if you add cross-linker, you get 3D polymer link, 3D polymer network. Then it will be more chemically and mechanically stable. We have 3D structure. So we also add some silicon. So we have silicon, as you see here. So when we add some silicon here, we have silicon, contains silicon here. But we can use this layer as the etching mask to etch into the bottom polymer layers for the later on pattern transfer. So we got silicon. And we also have the fluorinated compound to lower the surface energy. You can see here. So here, as you see here, we need the resist to have very low surface energy. When we have very low surface energy, this can be utilized by fluorinated compound. So we know that for the cooking ware, we used to use the Teflon. So that's Teflon. This one. So when we have the fluorine gives you then we get very low surface energy. So thank you.